Hey guys, happy snow day. Okay, so today what we're going to be doing is we're going to start talking about Taylor polynomials. So what a Taylor polynomial is it's a polynomial equation that approximates any function that we want it to. So what we're going to attempt to do today is write a polynomial that is going to approximate cosine. Um, so let's try to just write the equation of a tangent line. Let's start with the most basic polynomial, just a line. And then let's try to see how close we can get it to approximate cosine. And then we're just going to add more and more to try to make it approximate it even better. Okay, so here, if we look and try to write the equation of a tangent line, same questions. What two things do you need to write the equation of a tangent line? And that's still point and slope. So to find the point, we're going to plug x equals 0 into the function, and the cosine of 0 is 1. And now we want to find the slope of that tangent line, so we need to find the derivative. The derivative of cosine is negative sine of x. And then if we plug 0 into that derivative, we end up with 0. So now we know that the slope of our line is 0. So just in general, to write the equation of a tangent line, y minus y1 equals m times x minus x1. But if we simplify this, it's just y equals 1. So, and this is a really terrible approximation, but I think you can see that this is the tangent line to this curve. Oh, I missed a little bit. I'm going to try again. Tangent line to this curve at x equals 0 is just the line y equals 1. So if you notice, our approximation has the same y value and the same slope as the original function, but that's really all it has the same as. So let's try to think for a moment about what other property that we know of functions, of graphing a function, that we could use to make this like polynomial that we're writing have a better approximation to cosine, make it look more like cosine. And we could just kind of go up a degree. So if you notice, when you're writing the equation of a tangent line, you use the y value and you use the slope. Well, maybe let's use, so the y value is just like the value of f of x. And, oops. So the y value is just the value of f of x, and the slope is the value of f prime of x. Well, maybe let's increase this and look at what f double prime of x could add to this function. And then it could add some concavity. So maybe if we added some concavity to this function, it could do a better job of approximating cosine. All right, so maybe let's take a second and talk about why we want to approximate cosine. So cosine itself is, and all like the trig functions and other functions like natural log and e to the x, they're just annoying to like deal with. They're just annoying to like plug numbers into, annoying to differentiate and integrate, but polynomials are like very easy to take the derivative of, take the integral of, to plug numbers into it. So that's kind of why we're trying to write a polynomial equation that can approximate another type of function. All right, so let's try to like use the second derivative now. So if you notice, this function has the same y value, the same slope, so the same original function, the same derivative, and now let's make it have the same second derivative as cosine. So if we kind of, instead of writing like a tangent line, kind of write like a tangent parabola, kind of. So we're going to try to write the equation of a parabola that mimics cosine. So if we think about the original, like a general quadratic equation, it's just ax squared plus bx plus c. And then if we think about what it is that we're trying to approximate, well, that's just cosine. So now let's go ahead and take the derivative of each of these and then try to make them equal each other at the certain x value that we want at x equals 0. So if we take the derivative of just a general polynomial, just a general quadratic equation here, we're going to bring the 2 down, so it would be 2ax plus b. And then if we take the derivative of cosine, well, that's just negative sine. All right, so now let's move on and let's take the second derivative of this equation. So the second derivative of 2ax plus b is just 2a. And then the second derivative of cosine is negative cosine. All right, so now remember that we're doing this at x equals 0. So let's plug 0 into both columns of this and see what we get, and then try to like make A, B, and C work out to be the same values that like we want them to be, the same values of what cosine's y value, slope, and concavity would be. So it's on the next slide, but I already have it like written here, so I'm just going to kind of write that chart here. So if I look at f of 0, well, if I plug 0 into this function, do you see how you just get c? And if I plug 0 into this function, I get 1. So that I want these two columns to equal each other. So now that lets me know that c equals 1. All right, now let's do it with the next column. If I find f prime of 0, if I plug 0 into this equation here, do you see how you just get b? And if you plug 0 into the second derivative, do you see how you just get 0? So I want these two things to equal each other. So then that lets me know that b is 0. Now let's do the same thing with the second derivative. So if I plug 0 in for x in this equation here, you just get 2a. And if I plug 0 into this equation, I'm going to get -1. So now I'm going to try to make these two equal each other. So I'm just going to write that off to the side here. So 2a is going to equal -1. So what value of a would achieve this? And then you can see that a is supposed to be -1/2. So now that I know these values, I can plug them into a generic like polynomial or quadratic equation, and then I'll be able to draw a parabola that mimics cosine. So here I know that I've found that a is going to be -1/2, b is 0, and c is 1. All right, so then the quadratic approximation for cosine is just remember that a general quadratic equation is ax squared plus bx plus c. So we're just going to fill in the a, b, and c that we found. So now we know that our quadratic approximation is -1/2 x squared plus 0x plus 1. So if we just look at those two graphs, so I'm just going to scroll up to the first slide and try to graph this parabola. So if you want to write it, I don't know, a little bit, I mean, you don't need the 0 there. It looks kind of stupid with the 0 there. All right, so this is just -1/2 x squared plus 1. So you see how this is just like a parabola that's inverted, wider, and then shifted up 1. So I'm just going to draw that on my original cosine graph here. I'm just going to clear all this mess out. So just like it should be, do you see how like if I drew an upside down parabola that's a bit wider and shifted up by 1, do you see how, oh, I'm doing that not very well. Do you see how that would look? Oh God, it's so hard to draw on this thing. See how that would look a little bit like that? So that certainly did a better job than just a tangent line. A quadratic function would do a better job than just a line. So I hope that this kind of convinces you that if we did this for further and further derivatives, that this would do a better and better job of approximating it. All right, so now we're going to get a little crazy with this, and we're going to do it with a 6th degree one. I know you're groaning. I'm sorry. I know it's a snow day. But the good news is you don't have any homework tonight. All you have to do is watch this video. Okay, and if you have any questions, just come and see me in the check-in. All right, so now let's think about just a 6th word. I know this says quadratic approximation, but it's not. It's going to be something to the 6th power. So let's think about like what a function, a general polynomial to the 6th power would be. So that's just going to be ax to the 6th plus bx to the 5th plus cx to the 4th plus dx to the 3rd. This is annoying. Plus ex squared plus fx plus, I'm like, g. I couldn't remember what came next. That's embarrassing. All right, and we're trying to approximate the cosine of x. So now we're just going to do that whole thing again. We're just gonna, I should have scrolled this just a little bit. I'm just gonna scroll this just a little bit up. I don't think I'll be able to move that, but I think it'll be worth rewriting it so that I can have space down there. Okay, so now what I'm just going to do is I'm just going to keep taking derivatives of this just like I did with the other one until I get like down to just a constant. Sorry, bear with me. And then we're gonna write cosine here. Okay, and this isn't quadratic, this is a higher power. All right, so now let's just keep taking the derivative. You can kind of see what's gonna happen here. So if I go to take the first derivative, this is going to be 6ax to the fifth plus 5bx to the fourth plus 4, oh God, cx cubed plus 3 dx squared plus 2ex plus f. And then the g goes away. And now let's take the derivative here. So if you look, we're going to get negative sine of x. I'm going to do a different color just so it looks a little bit of contrast. All right, so now let's do this again. So let's take these powers down, take the second derivative. So 5 times 6, that's 30 ax to the fourth plus 20 bx to the third plus 12 cx squared plus 6 dx plus 2e. And now the f goes away because that's the constant. All right, so maybe I'll make a little rainbow. Oh, the yellow's not going to work. I'll do orange. All right, so now let's bring the next one down. So 4 times 30, that's 120 ax cubed plus 60 bx squared plus 24 cx plus 6d. All right, now I'm going to do that again. So now this is going to be 3 times that is 360 ax squared plus, this is kind of hard to read, but that's 120 bx plus 24c. Almost done. All right, so now if I'm going to bring this 2 down, it's going to be 720 ax plus 120b. And then this one's just 720a. All right. Oh, I forgot to do it on the other side. That's okay. I won't make all the colors match. You guys will kill me if I take that long. All right. So now let's take the derivative of negative sine. So that'll be negative cosine of x. Then the derivative of negative cosine is positive sine of x. And then I get cosine of x, negative sine of x, and then I'm just taking repeated derivatives if that wasn't clear, and then negative cosine of x. So now remember that we want these two things to equal each other. We want the like all these derivatives to have the same value as what like the original function would have. We want it to have the same y value, the same first derivative, same second derivative, same third derivative. This way I build a polynomial that mimics cosine more effectively. So we're just going to plug 0 into both the left and the right side of this and then make them equal each other. All right, so let's try that here. So if I plug 0 into both of these, do you see how on the left side of that, I just get g? And on the right side of that, cosine of 0 is 1. So that lets me know that g is 1. Now let's do it with the next derivative. So if I plug 0 into this one, then only f is left. So f, then if I plug 0 into this, the cosine of, or the sine of 0 is 0. So that lets me know that f is 0. So you can also do this. That's what like this chart down here is for. I just don't want to like, scroll and then all these things be in the wrong spot. Okay, so now let's do it with the second derivative. So do you see how if I plug 0 into all these x's, all those first terms are going to cancel out. And then I'm left with 2e. And then here the cosine of 0 is 1 times the negative is negative 1. So we already did this part though. We already know that the constant should be 1. The linear term should be 0. And then the quadratic term, if you set these two equally to each other. So I'm going to do that off to the side. So 2e equals negative 1. And we know that the quadratic coefficient should be negative 1/2. We kind of did that already when we found the parabola that approximates this. Now we're moving on to the third derivative. Okay, so if I look at the third derivative, so even though these steps look different, do you see how these constants still came out to be the same as they did in the last example? That's because that's like what parabola would still mimic this. That won't change. All right, so now if I plug 0 into this third derivative here, I get 6d. If I plug 0 in for x, then if I plug 0 in for this x, the sign of 0 is 0. So now that lets me know that d should also be 0. Okay, so now if I plug 0 into the fourth derivative, I'm left with 24c. So if I plug 0 into cosine, I get 1. So now I need 24c to equal 1. So then c has got to be 1/24. All right, let's go on to this one. So now if I plug 0 in for x, I'm left with 120b. And then if I plug 0 into sine, that's 0. So that lets me know that b is 0. One more. All right, if I plug 0 into x into this bottom one, there's no x, so it's just 720a. And if I plug 0 into negative cosine of x, I get -1. So that lets me know that a had better be -1/720 to build this polynomial. So now I have what all the coefficients should be, so I can plug them into the polynomial and it'll provide a a graph that mimics cosine. I wish I had this already set up for you, but I don't. Sorry. Okay, so now let's just try to write this p sub 6 there, means like a 6th degree polynomial. So I have everything I need to write a 6th degree polynomial that mimics cosine. All right, so here I have negative, oops, I'm not on annotate. Sorry. I have -1/720 x to the 6th, right? Remember that I'm going back and plugging these, I found all the values of these coefficients. So I'm going to go back then, I'm going to plug everyone in for what they should be. All right, so now b I found was 0, so I'm not going to have an x to the 5th term. All right, so then I know that c is 1/24, x to the 4th. D is not there, so that term's gone. E I know is -1/2, so I have -1/2 x squared. F is 0, so that term's gone, and then just +1. So I have built a polynomial that does a better job of approximating cosine than just a parabola. I know that I had these like leading questions of what we're going to do next with it, but I kind of want to do that in person. So I'm going to leave that to you for tomorrow or the next day in class, whenever that is. Okay, so the only other thing that I want to do with you guys really quickly is I just want to graph cosine, and I want to graph this, and I want to show you how, like, the job that it does. I'm just going to open up a Desmos. Maybe if this thing will stop fighting with me. Oh, I'm sorry. Okay, so I think that you're still seeing that. All right, so let's go to Desmos. Okay, so first I'm just going to graph the cosine of x, and then I'm going to graph this other polynomial. So -1 divided by 720 times x to the 6th plus 1/24 x to the 4th minus 1/2 x squared plus 1. So if you can kind of see, I'm just going to make this a little bit bigger and get rid of all this writing. So you can kind of see that like this does a pretty good job of approximating cosine like in its neighborhood. I'm just going to real quick add on the next one so that you can kind of see what's going to happen. I can't do this in my head, but I don't expect you to know how to do this yet, but I'm just going to show you what the next one is so that you can see how cool it looks. So don't worry about like where this is coming from yet. We'll explain that tomorrow. But do you see how like if I add on another one, it does a better job? Do you see how like if I added on the next one, it would then curve down and then it would curve up? It would just keep adding more curves so that it would look more and more like cosine. I hope you think that that's pretty cool. Like we built a polynomial that's looking like cosine. It's kind of crazy. All right, so that's all for today. Tomorrow we're gonna like take this the next step and kind of like figure out like why these numbers are the way they are and like figure out a way that we could do this for any function that we wanted. Okay, guys, enjoy your the rest of your snow day, and no homework tonight. Thanks. Bye.